Okay, I apologize for the poor audio quality. I don't have my good mic with me. This is going to be a little bit off the cuff anyway, but I just wanted to talk over a couple of issues around the extension problem of rotating an image by an arbitrary angle. So it seems like this is a question about, like a mathematical question about how to do arbitrary rotation. So how can you take a point P, rotate it through an arbitrary angle theta, and end up at a new point P prime? Let's assume that we actually have a function that does this already. So let's call it rotate. You give it like a pair of xy coordinates, and it will give you the rotated corresponding xy coordinates. So let's pretend that's solved. We'll come back to kind of how you can do this, and then also how you can do this efficiently in a minute. A couple of notes. So the first thing is, where's the origin? So in this picture, I've drawn the origin in its usual mathematical location. If you're going to use the row and the column as the coordinates for your pixels, in that case, we've got it up here. And so rotating through a positive angle is going to rotate everything kind of this direction, which is also probably not how you want your image to rotate. What you probably want it to do is you want it to rotate around the center. So my first note is that if you already have a way of rotating around the upper left-hand corner, let's say, but you want to rotate your whole image around its own center, an easy way to do that is to, let's say, translate by this vector. So translate left by half the width, and then translate up by half the height. So translate by negative width over 2 and negative height over 2. Then you can rotate, because after you've moved the image, now rotating around the upper left-hand corner is the same as rotating around the middle, because you've actually moved the middle to be in the upper left-hand corner, and then translate back afterwards. So then you translate back by width over 2 and height over 2. So that's one issue, rotating around the middle. Here's another issue. This has to do with the quality of the output. So you could imagine kind of two ways of doing this. If you have a source image and you're going to have a target image, so this is supposed to be the rotated version of source. One thing you could imagine doing is looping over every single pixel of the source one at a time. Apply this transformation where you translate, rotate, translate. And then each pixel here is going to get mapped onto some pixel over here. So let's just take an arbitrary one from the middle here. So if this is P, here's the middle, and P ends up in the target over here, P prime, what I'd do then is I'd take the pixel value at P, color, black and white, or whatever it was, and then literally just copy that exact pixel value over here to P prime. The problem with that is, depending on what angle you're rotating, you're not going to end up, your coordinates at P prime are going to end up being exactly integers. And so you might end up having some visual artifacts where maybe there are some pixel values that don't get assigned a color value at all from the source, and other pixel values may get kind of overwritten because they get assigned two different pixel values from the source. So a different way of doing it is doing the reverse mapping, or we might say inverse mapping. Instead, loop over every single pixel of the target, and then, like whatever you did up here, apply the inverse function. So instead of translating, rotating, translating, instead you would translate the other way, do the inverse of whatever your rotation was, and then translate back again. And so what you're doing there essentially, so let's think about it that way. So now we've got, this is P and this is P prime. So if I'm looping over each pixel of the target and I eventually reach this arbitrary P, I'll figure out, oh, here's the coordinate that was supposed to map there. But instead of just copying it over, now what I can do is I could sample a whole bunch of pixels in that region, find the average, or maybe even better, the weighted average, where you give the center value more weight. And then that's the value that I'll copy over to the target. And so now you're sure that every single target pixel is getting assigned a value. So that's the second issue. So the third issue is, how do you actually do the rotation? So there's like a bunch of different ways you could do this. Let's pretend that you're... So you could do this just using math that you learned in Algebra 2 trig. So like, let's just think that through for a second. So if I've got P here, and I want to try and rotate it through some fixed angle theta to get P prime, how's that going to work? So let's call this xy, let's call this x prime, y prime. Okay, so an easy way to do it is to think about, like, xy are rectangular coordinates. What if you're going to convert this to polar coordinates, add an angle, and then convert back to rectangular? So, for example, let's call this hypotenuse distance r. So you know r is x squared plus y squared because it's the hypotenuse. Let's call this alpha. So alpha should be so like tangent of alpha is this over that. This is just y, this is just x. So tangent of alpha is y over x, therefore alpha is the inverse tangent of y over x. Okay, so this is like the class, standard conversion into polar coordinates where we've got a distance and an angle. So once you've got your alpha, now we can compute this new angle as alpha plus theta. And then to go back and find what's x prime, y prime. So if I have the cosine of, well, I guess let's do it this way. So if I've got cosine of alpha plus theta, that's that entire angle, by SOHCAHTOA, cosine should be this leg divided by this. But this is still just the same radius because we rotated the point. So the hypotenuse distance shouldn't have changed. So that should be x prime over r. Therefore, x prime is r times cosine alpha plus theta. And then similarly, y prime is r times sine of alpha plus theta. So that's just all kind of Algebra 2 trig, pre-calc-y kinds of stuff. And that would work just fine. The problem with this is it's not terribly efficient. Calculating a lot of, like, for every single pixel, calculating the inverse tangent and then calculating the cosine and the sine of the results is going to be pretty wasteful. If you look this up on the internet, you're likely to see something like this, or if you studied a little bit of linear algebra, or if your pre-calc class did this kind of thing. So like this problem turns out to work out very nicely in terms of taking a vector and multiplying it by a matrix that represents a certain type of transformation, in this particular case, a rotation. And so like this is kind of the formula for a matrix that corresponds to a rotation counterclockwise or anti-clockwise through an angle of theta. What's nice about this is when you know what angle you want to rotate through, you can figure out what number is each of these, and then you never have to calculate them again. You've just got a matrix with some fixed values. And then if you know about matrix multiplication, what this ends up being is you take your xy, you multiply it here to get your x prime. So let's do it this way. So x prime, y prime. So I'd have x times cosine theta plus, and then I'm going to multiply y here. So y times negative sine theta. That's kind of an ugly way to write it. So that's x prime. And then y prime is going to be x times sine theta. I guess let's do it that way. So minus y cosine theta. So in other words, like this gives you an equation for going directly from your old xy coordinates along with some trig functions of your angle to what your new x coordinate should be. And same thing for y. And this is a lot faster because you only have to use the trig functions once to get your matrix, and then after that, it's all multiplication. So that's really, really fast. The downside is maybe you didn't actually know anything about that, and it's also a little bit mysterious why this works at all. Okay, shoot, I gotta go. But so the planned part 3 for this video was kind of re-deriving that same result, but not in terms of matrix multiplication and vectors. Instead, it's pretty easy to re-derive that just by thinking about the geometry of multiplying complex numbers on the complex plane. And you can kind of get that result out very, very cleanly. So I'll make a new video that kind of walks through that, maybe today or tomorrow.